when some wag said it's feasible to think responsibly about one thing and not the other. Well, I could see from that one sentence that that was perfectly ridiculous, and it pushed me further into my natural drift, which was into learning all the big ideas and all the big disciplines.
Welcome, welcome, welcome to the deep dive. Today, we're embarking on, well, an absolutely fascinating journey, plunging headfirst into a topic that tech visionaries like Mark Andreessen and Elon Musk aren't just talking about. They're actually calling it the next industrial revolution. Robotics. Specifically, we're going to try and unpack what's known as embodied AI. Now, at its heart, pretty much every single robot, from the smallest vacuum cleaner to the most advanced humanoid, operates on a surprisingly simple yet really profoundly powerful foundational concept, the sense-think-act loop. It sounds straightforward, right? But it underpins everything we're about to explore today.
Yeah, and that sense-think-act loop is indeed the bedrock, and it really defines why robotics isn't just one field, but a vibrant interdisciplinary fusion. It sits squarely at the crossroads of computer science, mechanical and electrical engineering, and of course, artificial intelligence. Our mission today really is to cut through some of the complexity, connect those, intricate dots for you, and pull out the most vital insights from our source material. We want to give you that shortcut to being truly well-informed, allowing you to not just understand, but really grasp this rapidly approaching world of embodied AI, hashtag the core idea, embodied AI, and Moravec's paradox.
Okay, let's unpack this crucial term right away then. What is embodied AI? Because when many people think of AI, they often picture, a supercomputer playing chess or maybe a large language model generating text, something abstract. But embodied AI is, well, fundamentally different because it refers to artificial intelligence systems that possess an actual physical body. We're talking about robots, autonomous vehicles, drones, pretty much anything that can directly sense the real world with its own senses and then act within that real world through physical interaction. It's not just software on a screen.
Exactly. It has a body. It lives in the world.
And the journey to this concept actually began surprisingly early, didn't it? Back in the 1960s with a groundbreaking project called Shaky.
Shaky, yes.
Shaky wasn't just another lab experiment. It was like a pivotal moment in AI history. It was the very first robot that could truly perceive its surroundings using onboard sensors, think really early cameras and rangefinders.
Very primitive by today's standards, yeah.
Yeah, right. And then, crucially, make autonomous decisions based on what it perceived. Shaky's debut was a real turning point because it moved AI beyond the confines of purely theoretical simulations or just game playing. Suddenly, AI wasn't just abstract logic. It was embodied in a physical machine, navigating real hallways, avoiding actual obstacles, and planning its own movements. It showed that intelligence wasn't just about abstract thought, but about acting in the physical world.
And building on that initial spark, a truly influential idea emerged in 1991 with Rodney Brooks's paper, Intelligence Without Representation. Brooks, a brilliant roboticist, really challenged the prevailing AI wisdom of the time. See, many thought you needed to build these incredibly detailed, complex, abstract models of the entire world inside a robot's digital brain before it could do anything intelligent.
Like a perfect internal map.
Exactly. But Brooks argued, quite compellingly, that true, robust intelligence actually emerges from a robot's direct, physical interaction with its environment. It's not just about planning based on that perfect internal map. It's about the continuous feedback loop of sensing and acting in the messy, unpredictable, real world. He emphasized that hands-on, real-world experience, sensing, acting, adapting physically is absolutely fundamental to developing intelligence that is both robust and adaptable. It was, well, a profound philosophical shift that continues to influence robotics profoundly today. It really pushed us from purely theoretical AI towards practical, physically grounded intelligence.
That makes so much sense. If you think about how a human baby learns, it's not by, reading a textbook on physics.
No, not at all.
It's by reaching, grasping, falling, bumping into things, exploring its physical environment. So if we connect that historical context of Shaky and Brooks to the present day, you can really see how this concept of embodied AI is driving a completely new wave of robotics. Today's robots are leveraging the incredible breakthroughs we've seen in artificial intelligence, like deep learning and reinforcement learning, to learn by trial and error directly in the real world, much like that baby.
Precisely. And this leads us to one of the most, well, fascinating observations in the field, known as Moravec's paradox.
Ah, yes, the paradox.
It essentially states that tasks humans find easy, like walking across a crowded room, picking up a pen, understanding conversation, or even just seeing and recognizing objects. These are incredibly hard for robots. Yet, tasks we humans find hard, like solving complex mathematical equations, performing vast data analysis, or beating a grandmaster in chess, can be relatively easy for AI.
It seems completely backwards, doesn't it?
It does. And this paradox wasn't just a quirky observation. It was a fundamental challenge to early AI's assumptions. For decades, many researchers genuinely believed that if we could just crack the code on highly abstract, logical problems like chess, physical intelligence would sort of naturally follow. But Moravec's paradox revealed the immense, often invisible complexity of what we consider easy in the real world, all the messy, unpredictable nuances of perception and motor control. It forced a profound shift in AI research, pushing us away from purely theoretical symbolic systems towards these embodied, learning-based approaches. It really underscored that true intelligence isn't just about logic, it's about direct, real-world interaction.
So why were those easy for humans tasks so difficult for so long?
Well, for decades, despite having incredible computational power, robots genuinely struggle with what we consider basic sensor-motor skills, because frankly, perception and physical dexterity demand enormous computational resources and incredibly nuanced learning. Just think about how much information your brain processes instantly just to walk across a room without tripping. Yeah, you don't even think about it.
Exactly. But now, thanks to those breakthroughs in AI, especially deep learning, and the dramatic improvements in sensor technology, robots are finally beginning to tackle these easy for humans, hard for robots tasks with much greater proficiency. We're seeing specific, almost astounding examples everywhere. Highly accurate, vision-based object recognition that can distinguish between, say, various fruits or tools, bipedal robots that can not only walk but also run and maintain balance even when, shoved.
Like those Boston Dynamics videos.
Precisely. And incredibly gentle, precise grasping of delicate objects like a raw egg or a crumpled piece of paper. As Mark Andreessen has insightfully pointed out, we are now at the point where physical AI is poised to scale up dramatically in the coming years. This isn't just incremental improvement. It indicates a truly transformative period ahead, potentially driving, as you said, a new industrial revolution right before our eyes. #tag sensing the world, perception, and localization. Okay, so if a robot is going to act intelligently in the physical world, it obviously needs to understand that world. It first needs to sense its environment. How do they actually achieve this? It sounds basic, but it must be complex.
It's fundamental. A robot must perceive its surroundings to operate intelligently. Without that sensory input, it's essentially blind and deaf, right? Unable to distinguish a wall from a doorway. So to achieve this, robots are equipped with a wide, sophisticated variety of sensors that, in many ways, mimic and sometimes even extend our own senses.
Like what kind of sensors are we talking about?
Well, think of cameras for visual input, and often not just one, but multiple, providing stereo vision for depth perception or even 360-degree views. Then there's LiDAR.
LiDAR, right. You see that spinning thing on self-driving cars?
Exactly. It uses laser pulses to measure distances and build incredibly precise 3D maps of an environment, almost like a super accurate radar system using light. Sonar uses sound waves for similar distance sensing, often useful in closer proximity or, say, underwater. Then you have tactile sensors, embedded in their skin or grippers, giving them a sense of touch, which is crucial for delicate manipulation. GPS, of course, provides global positioning outdoors, and even microphones contribute, allowing robots to perceive sound, maybe locate where a sound is coming from. All of these are meticulously designed to gather vast amounts of data about the world around the robot and, just as importantly, about the robot's own internal state, its joint angles, its orientation, maybe its temperature, things like that.
Okay, so they're gathering tons of data, but just collecting raw sensor data isn't enough, is it? It's just noise, like you said. Making sense of that data, that must be where the real challenge lies.
Absolutely. That's where the real sophistication comes in. It requires incredibly advanced computer vision and sensor processing techniques to interpret what's actually happening in their surroundings. For instance, an early robot vision system might have used classic algorithms like co-transforms to meticulously detect lines and circles in an image. Or it might look for specific fiduciary markers like April tags, which are basically specialized QR codes designed to give robots precise, unambiguous reference points in their environment, useful in structured settings like warehouses.
But those sound kind of limited, maybe brittle.
They were, in many ways, which is why modern robotics truly shines, and where we've seen a massive leap is in its reliance on deep learning. Specifically, convolutional neural networks, or CNNs, have completely revolutionized perception. These AI models, trained on literally millions of images, have vastly improved the accuracy of object recognition. They allow a robot to not just see a shape, but definitively identify it as a chair, a bottle, or a person. Yeah, they enable sophisticated scene classification, understanding the layout of an entire room, and even accurate people detection and tracking, far surpassing what was possible with those earlier handcrafted methods. It's like moving from a blurry black and white sketch to a high-definition color photograph in terms of a robot's ability to understand its visual world.
That immediately raises a critical point, though. If robot perception, like our own, is inherently imperfect, I mean, think of weird lighting conditions, sensor noise, or just incredibly cluttered environments, how do they cope with that uncertainty? We humans, we're constantly making educated guesses based on incomplete information, right?
Absolutely, and that's a fantastic question because it highlights a key approach. That challenge has led to what we call the probabilistic approach in robotics. Instead of demanding 100% certainty from their sensor readings, which is often impossible, robots are designed to maintain beliefs with probabilities.
Beliefs with probabilities, like odds.
Kind of, yeah. Think of it like driving in heavy fog. You don't see everything perfectly, but your brain is constantly making educated guesses. That blurry shape might be a car, maybe an 80% chance I should probably slow down. Robots employ a very similar principle. So, a self-driving car doesn't know with absolute certainty what every single pixel in its camera feed represents. Instead, it uses these probabilistic models to infer, okay, there's an 80% chance that object is a pedestrian, or a 95% chance that's a stop sign.
Okay, so it's working with likelihoods.
Exactly. This empowers them to make intelligent, robust decisions, even when the data is incomplete or ambiguous, much like we do when navigating our own uncertain world. And building on these foundational sensing abilities, you get into higher-level perception tasks like robust object recognition in real-world clutter, detailed scene understanding, knowing the layout and functional areas of a room, and even recognizing human activities, which is, as we'll discuss later, vital for safe and effective human-robot interaction.
Right, so once a robot can actually see and understand its environment, even probabilistically, the next fundamental step is for it to know where it is within that environment. What's the big idea here? This sounds crucial.
Oh, it's absolutely crucial. It's the core problem of how robots know their own precise position and orientation. For any mobile robot, whether it's a small vacuum cleaning robot diligently mapping your living room or a massive autonomous truck navigating a mine, it's vital for it to localize itself, to know its position. And very often, it needs to concurrently build a map of the environment it's in, especially if it's exploring an unknown space.
So mapping and knowing where you are on the map.
Exactly. And this is where a truly major robotics concept called SLAM comes into play. SLAM stands for Simultaneous Localization and Mapping.
SLAM
algorithms are ingeniously designed to tackle this sort of chicken and egg problem.
Oh, yeah.
How do you build a map if you don't know where you are, and how do you know where you are if you don't have a map?
Right. Sounds like a paradox itself.
It kind of is. SLAM allows a robot to use its sensor data, say LiDAR scans or camera images, to concurrently build a map of an unknown environment while estimating its own location within that newly created map. It's a bit like exploring a dark cave for the first time. You're sketching the map as you go and using your developing map to figure out where you are on it.
So how does it actually do that? How does it combine the information?
Well, to achieve this, robots typically combine multiple, sometimes conflicting sources of information for localization. They might use wheel odometry.
Which is just counting wheel turns, basically.
Yeah, exactly. It provides a rough estimate of distance traveled, but it's prone to drift over time, like if the wheels slip a little. You can't rely on it alone over long distances. So to refine this, they use landmarks or distinct visual features observed by cameras or laser scanners as precise reference points. I see that same doorway again. I must be back near where I started. They also integrate data from inertial sensors IMUs, which measure acceleration and rotation, giving them a sense of how their body is moving, independent of the wheels.
Okay, so multiple sources. Then what?
Then, sophisticated sensor fusion techniques, often employing probabilistic filters like Kalman filters or particle filters, merge all these diverse inputs. They weigh the different pieces of evidence to produce the best possible, most statistically likely estimate of the robot's position and orientation.
Can you give an example?
Sure. Think about the Mars rovers, like Curiosity or Perseverance. They combine their wheel odometry data with visual tracking of terrain features, essentially identifying unique rocks or craters they've seen before to accurately know how far they've moved and in what direction across the Martian landscape. They're truly figuring out where am I and what does the world around me look like, all internally, because there's no GPS on Mars.
Wow, that's incredible. So this SLAM capability is fundamental.
Absolutely fundamental. It underpins a robot's ability to navigate effectively, to avoid obstacles reliably, and to reach its target location. Classical SLAM research has been a big idea in robotics for decades, enabling everything from the humble Roomba vacuum to complex autonomous drones to operate without relying on external GPS. They build their own world model and track themselves within it. And the field is still advancing rapidly. More modern approaches are even using deep learning to recognize places or perform visual SLAM even more robustly in really dynamic and complex real-world settings, which is a massive leap forward. Ultimately, mapping and localization give a robot spatial awareness. It's the equivalent of our human sense of location and spatial memory, absolutely crucial for intelligent action in the physical world. Tag thinking and moving motion planning, kinematics, and manipulation.
Okay, this is fascinating. So the robot has its senses working, it knows where it is in the world, probabilistically at least, and it understands what's around it. But then comes the really complex part. How does it actually decide what to do next? How does it figure out where to go and how to get there?
Right. It's one thing to see an obstacle, another entirely to figure out the most efficient, safest way around it. This is the realm of motion planning, often called path planning. At its core, it's essentially the process of deciding on a safe path or a precise sequence of movements to reach a specific goal without colliding with anything in its environment.
Okay, so like planning a route on a map, but for the robot's immediate surroundings.
Exactly. Imagine an autonomous car planning a trajectory to change lanes smoothly and safely on a busy highway, considering all the other cars. Or a mobile robot figuring out the optimal, maybe the most energy-efficient path through a cluttered factory floor to reach a charging station. These aren't simple decisions. Robots use incredibly sophisticated path planning algorithms to search for a safe route around all the perceived obstacles in their internal map or representation of the world.
What kind of algorithms are we talking about?
Well, two influential families of algorithms used here are sampling-based planners, like RRT, which stands for Rapidly Exploring Random Tree.
RRT.
These work by randomly sampling millions of possible movements and then building a tree of reachable states, eventually connecting the starting point to the goal while navigating around obstacles. It's surprisingly effective in complex spaces. Another common and powerful approach is grid-based planning, such as the famous A-search algorithm. This searches for the optimal path on a discretized grid representation of the environment, sort of like finding the shortest route on a city map by exploring adjacent streets.
A search. I've heard of that one in computer science.
Yep, it's a classic. And the output of these planners isn't just a vague idea. It's a precise path or trajectory, a series of waypoints and movements, which the robot's control system then has to meticulously execute.
Right, so that covers how a robot figures out a safe route on a map, like for a wheeled robot. But what about something more complex, like a human-like robot leg or a multi-jointed robotic arm? Their movement isn't just about navigating a flat plane, is it?
Not at all. They operate in 3 dimensions, with many joints and limbs. For robots that move in continuous space, like these articulated arms or legged robots, planning isn't just about simple geometry. It also delves deep into kinematics and dynamics, which are fundamental studies of motion and the forces involved. Planning a robotic arm's motion from one pose to another while avoiding hitting anything and respecting the physical limits of its many joints is a similar problem to mobile robot navigation, but it operates in a much higher dimensional configuration space, essentially the abstract space of all possible joint angles.
Higher dimensional space. That sounds complicated.
It is. Motion planning algorithms are designed to handle these incredibly complex scenarios. For instance, figuring out how a robotic manipulator can precisely reach around an obstacle to grasp an object without bumping into anything on its way. It's like a high-stakes game of Twister for the robot's joints.
Then what about moving things? People walking around?
Great point. Real-world navigation and manipulation often involve dealing with dynamic environments where things are constantly moving, people walking, other robots, objects being moved, and inherent uncertainty. So modern navigation systems are designed to continuously replan on the fly as new obstacles appear or as the environment changes. This concept is known as dynamic replanning or trajectory optimization. They don't just make one plan and stick to it blindly.
They adapt in real time.
Exactly. And there's often a hierarchical approach to this. You might have high-level global planning that computes a broad route, like navigating across a building using a pre-built map. And then you have low-level local planning that handles immediate reactions to obstacles, like dodging someone who suddenly steps out, or fine-tunes the robot's motion based on its own physical constraints. Think of it as deciding your overall road trip route versus reacting to a sudden brake light right in front of you on the highway. The key idea is that navigation isn't just static path planning. It demands real-time adaptation and often combines sensor-based reactive behavior like immediate obstacle avoidance reflexes with a meticulously planned path.
Okay, that planning part is intense, but that brings us to the actual execution. How does a robot actually control its body to follow those plans precisely? Whether it's a wheeled chassis, a complex robotic arm, or a humanoid robot with legs, its physical form must be controlled with incredible precision to execute those carefully computed paths.
This is where kinematics and dynamics become absolutely central. Kinematics, as we touched on, is the study of a robot's geometry of motion, looking at how its parts move in space without considering the forces involved. It's like drawing the blueprint of how a limb can extend or bend based purely on its joints and links.
Just the geometry?
Right. Dynamics, on the other hand, does consider the forces and torques that cause a result from motion. So if kinematics is the blueprint of how a robot can move, dynamics is understanding the power needed to make it move, how much force a motor needs to apply to lift an object, or how inertia affects a robot as it swings its arm quickly. It's the essential physics behind the movement.
So you need both.
Definitely. Every articulated robot, like an arm with multiple joints or a legged robot, can be described as a kinematic chain, basically, a series of rigid links connected by joints. A really big concept here is that robots use mathematical kinematic models of their own bodies to translate between joint space, which is simply the angles of each individual joint, and Cartesian space, which refers to the familiar XYZ coordinates of a specific point in 3D space, like the robot's hand or end effector.
Joint space to Cartesian space.
Okay. And there are standardized ways to do this. The classic Denevit-Hartenberg convention, for example, is a standardized method to define a robot arm's length lengths and joint axes, making these kinematic calculations consistent across different robot designs. This might sound a bit dry and academic, but it was absolutely critical for the field's progress, providing a kind of universal language for describing robot geometry.
So these models let them calculate movement.
Exactly. Using these models, a robot can perform what's called forward kinematics, computing where its hand or end effector is located in 3D space, given all the current angles of its joints. That's relatively straightforward math. Even more critically, it can perform inverse kinematics, figuring out what specific joint angles are needed to place his hand at a desired target location in 3D space. I want my hand here, so what angles do my shoulder, elbow, and wrist joints need to be?
Inverse kinematics. That sounds harder.
It can be much trickier. Sometimes there are multiple possible joint configurations to reach the same point. Think about how many ways you can touch your nose. Sometimes there's no solution at all if the desired location is physically out of reach. But it's absolutely fundamental for controlling manipulators and legged robots. It's how a robot knows how to precisely bend its arm to pick up that specific cup off the table.
Okay, so the plan is made, the kinematics are calculated, now make it move smoothly.
Right, and that's where control systems come in. They are what truly enable a robot to execute those planned motions smoothly and accurately, turning those theoretical blueprints and calculations into physical reality. At the simplest level, you have feedback control, often utilizing something like a PID controller, which stands for Proportional Integral Derivative. It continuously adjusts the motor commands based on the error between the robot's current state, where it actually is, and its desired state, where the plan says it should be.
Like a thermostat, adjusting based on the difference.
Exactly like a thermostat, but usually much faster and more complex. For instance, if a wheeled robot is programmed to follow a straight line, but its sensors detect it's drifting slightly off, a PID control loop will immediately calculate and send a correction to its steering motors to bring it back on track. It's a constant loop of sense the error, calculate correction, adjust action.
And for more complex robots, like arms or legs.
For more complex robots, simple PID might not be enough. You often use model-based control algorithms. These incorporate the robot's dynamics model remembering. That includes things like gravity, inertia, friction, to precisely control, say, a robot arm as it moves quickly to a target position, accounting for all the physical forces at play to ensure smooth and accurate motion.
What about balance, like those walking robots?
Yes. An incredibly important subset here, especially for dynamic robots, is robotic balance and locomotion control. For a bipedal robot to walk without falling over, or for a drone to stay airborne and stable despite wind gusts, its controller must constantly rapidly respond to disturbances to maintain stability. This isn't just about following a pre-planned path. It's about real-time, instantaneous reactions to maintain equilibrium. It's incredibly challenging.
I bet.
And there's a huge body of robotics research dedicated to even more advanced control methods. Things like optimal control, which figures out control inputs that optimize a specific performance criteria and maybe move the fastest or use the minimum amount of energy. Or impedance control, which is really important for safety. It enables safe and compliant interaction with the environment or with humans, allowing a robot arm to give a little if it bumps into something, rather than rigidly resisting and potentially causing damage or injury. The bottom line is that actuation and control are what turn plans into action. No matter how brilliant a plan a robot has, it needs well-tuned control loops and a deep understanding of its own mechanics to actually move its motors, joints, or wheels to achieve the desired outcome smoothly, accurately, and safely.
Okay, so they can move themselves. But beyond just moving themselves through space, robots are increasingly designed to do things, right? To actively interact with the world around them. So what about the critical area of interacting with objects?
Yes, this brings us to robotic manipulation. It's broadly defined as a robot physically interacting with objects, grasping them, lifting them, assembling parts, pushing things, pulling things. The classic image, of course, is that industrial robot arm you see on an assembly line, precisely welding a car chassis or placing tiny components onto a circuit board with superhuman speed and precision.
Right, the factory robots.
But manipulation introduces a unique set of challenges, because the robot must now handle the external properties of objects, their specific shape, their weight, their texture, how slippery they are, their dynamics, not just move its own body parts.
Grasping seems like it would be really hard. How do they know how hard to squeeze?
Grasping is a central and surprisingly difficult problem. How can a robot hand or gripper reliably pick up objects of vastly different shapes and sizes, from a squishy tomato to a rigid metal block? This entails finding stable grasp points where to put the fingers and applying just the right amount of force. Not too much to crush it, not too little so that it slips and gets dropped.
Like threading a needle.
In a way, yes. Robots often use sophisticated force-torque sensors, usually located in their wrists, or highly sensitive tactile sensors on their fingertips to get feedback and adjust their grip in real time. It's very much akin to how we humans subtly adjust our hand and fingers when picking something up, unconsciously sensing its weight and texture through our touch receptors and modulating our grip force accordingly.
So they need that sense of touch.
It's incredibly helpful, yes. And beyond just the initial grasp, big ideas in manipulation also include trajectory planning specifically for arms, which means planning motions in incredibly tight, cluttered spaces without collisions. It's often like solving a complex 3D puzzle with a multi-jointed limb just to reach the object. There's also contact dynamics, which involves understanding and precisely controlling the forces that occur when the robot makes contact with an object or a surface, not just for grasping, but for tasks like pushing a box, sliding an object across a table, or carefully inserting a peg into a hole during assembly. And remember those kinematic models we talked about. They get extended to include the object the robot is holding, effectively creating a temporary, larger, combined mechanism that the robot must control as one unified system.
Wow. And how is this field advancing? Is it still mostly pre-programmed?
That's where things get really exciting. In recent years, manipulation has been absolutely revolutionized by learning-based approaches, particularly deep learning. Robots can now learn grasping strategies through trial and error, sometimes practicing on thousands of different virtual objects and highly realistic physics simulations before attempting it in the real world. This often involves deep neural networks that can look at a camera image of a bin of parts and predict good grasp points directly, without needing a perfect 3D model of every object.
Learning from experience, like we talked about earlier.
Exactly. And there are also significant efforts in what's called general-purpose manipulation. Imagine a humanoid robot in a kitchen that can pick up various utensils, a knife, a spatula, a cup open drawers, operate appliances, or use tools, all with the same two hands. This requires incredible adaptability and robust perceptual skills, far beyond a typical industrial arm that does the same repetitive task over and over.
So aiming for human-like versatility.
That's the goal for many researchers. Another rapidly growing subfield trying to achieve this is soft robotics. This involves using flexible, compliant materials to build robot hands, or even tentacles that can grip objects more gently and passively adapt to their shape, contrasting sharply with traditional rigid metal grippers. Think of an octopus arm versus a pair of pliers. While achieving true human-level dexterity, especially for novel, previously unseen objects, remains a huge open challenge, mastering manipulation is truly key for robots to perform useful physical work in our homes, hospitals, warehouses, and countless other everyday environments beyond the structured factory floor. #the brains and the team learning, interaction, and systems.
So we've covered the physical aspects, sensing, planning, moving, manipulating. But how do robots get smarter? How do they adapt to brand new situations without someone having to explicitly reprogram them for every single possible scenario? That seems like the real AI part.
You're right, that's where the intelligence really scales up. Historically, as we mentioned, many robot behaviors were handcrafted by engineers. Someone painstakingly programmed every single sequence of movements or manually tuned a controller through endless trial and error. It was incredibly laborious. But modern robotics is increasingly incorporating machine learning, and this is a true paradigm shift. It allows robots to learn from data or direct experience, rather than just following pre-programmed rules written by a human.
Okay, so machine learning for robots. What does that look like?
One of the key techniques here, which has shown amazing results, is reinforcement learning, or RL, applied directly to robotics. The basic idea is that robots can learn complex motor skills through trial and error, receiving virtual rewards or penalties for successful or unsuccessful outcomes. It's much like training a dog with treats, but for robot actions.
Learning by doing, essentially.
Exactly. For example, an RL algorithm might train a robotic arm to slide a block to a target position simply by letting it try many different random motions, observing the outcome, did the block get closer, and then reinforcing those actions that led to success. Deep reinforcement learning, which combines RL with deep neural networks, often trained first in simulation and then fine-tuned on the real robot, has produced truly striking results. We've seen robots learning to walk, run, jump, do backflips, open doors, or manipulate objects with incredible agility and nuanced skills that would be impossibly hard, maybe even literally impossible to script manually, step by step.
Right, like you said, embodied AI really benefits from that literal physical feedback. A robot learning to walk by actually stumbling and falling.
And then using that failure data to improve its balance control policy for the next try. That kind of iterative dynamic learning is only truly possible when the AI has a body to experiment with in the real world, receiving direct sensory input about its failures and successes. Simulation helps speed it up immensely, but real-world experience is often key.
Are there other ways they learn besides RL?
Oh yes. Beyond reinforcement learning, another powerful paradigm gaining immense traction is imitation learning, sometimes called learning from demonstration. Here, robots can watch a human perform a task, maybe through a camera, or even be physically guided through the motions by a person holding the robot's arm. The robot then learns to replicate that demonstrated task itself.
So learning by watching or being shown?
Precisely. This significantly lowers the burden of programming every minute detail, making robots much faster and easier to deploy for new tasks, especially complex ones. For instance, a robot could learn how to set a dinner table by being teleoperated through the motions just a few times by a person. Then, ideally, it can generalize that learned pattern to new situations, perhaps setting a different table or using slightly different dishes. This is an enormous step towards more flexible and user-friendly robots.
That sounds much more practical for everyday tasks.
It really is.
Yeah.
And robotics also strongly intersects with the broader fields of computer vision and deep learning in enabling what we call semantic understanding of scenes. This is a step beyond just recognizing objects. It means the robot doesn't just see a collection of pixels or a point cloud. It understands that it's looking at a chair, which is something you can sit on, or it can identify which specific objects in a scene might be fragile or hot and therefore require careful handling. It adds meaning to perception.
Giving the robot context.
Exactly. And what's particularly fascinating here and truly cutting edge right now is the emerging role of large language models, LLMs, like the ones powering ChatGPT. There's incredible research work connecting sophisticated language understanding directly to robots. This could enable them to take high-level, ambiguous human instructions like, go to the kitchen and grab me a cold drink, and break that down into concrete action steps, or even use common-sense reasoning derived from the LLM to handle unexpected situations.
So you could just tell the robot what to do in plain English.
That's the dream. These are still early-stage experiments, but they represent how incredible advances in AI, initially developed for text or images, can directly plug into and profoundly enhance a robot's ability to reason, plan, and act more intelligently and flexibly. Ultimately, learning and adaptation are truly big ideas, pushing robotics forward, making robots more autonomous, more robust, and more general purpose by leveraging vast amounts of data and experience, rather than being confined only to explicit, laboriously hand-coded programming.
That's a huge leap, moving from pre-programmed machines to truly adaptive learners. Now, as robots inevitably move beyond those controlled factory environments and increasingly into our homes, offices, hospitals, and streets, how do we ensure they play nice with us? That seems critical.
Oh, absolutely critically vital. This is where the field of human-robot interaction, or HRI, comes in. It's an entire area of research that asks a profound and complex question. How should robots behave around people to be safe, useful, and importantly, socially accepted? A really big idea here is that robots need to be acutely aware of and responsive to human presence, our behaviors, and even our subtle social norms.
Social norms, like robot etiquette.
Pretty much. For example, a service robot moving through a crowded hallway shouldn't just barge through. It shouldn't follow a person too closely, making them uncomfortable. It should ideally anticipate human movements, yield right-of-way when appropriate, and generally demonstrate socially acceptable navigation behavior, much like a polite pedestrian would. Getting this right is surprisingly hard.
I can imagine. So they need better perception for that.
Yes. Successful HRI requires advanced perception capabilities that go beyond just basic obstacle avoidance. It needs reliable human detection and tracking, understanding where people are and where they might be going, and potentially even recognizing human gestures, like a hand wave meaning stop or go ahead, or even interpreting facial expressions to gauge a person's mood or intent. Many research robots achieve this using specialized sensors like depth cameras, similar to how the original Microsoft Kinect was widely used in HRI research to track people nearby and understand their posture and movements in 3D.
Okay, so they need to be socially aware movers. What about communication?
Beyond just safe movement around people, HRI encompasses a wide range of sophisticated communication modes between humans and robots. This could be through natural speech, utilizing advanced voice recognition and natural language dialogue systems, so you can literally talk to your robot helper and it can talk back meaningfully. It could be through screen interfaces with intuitive menus and graphics, or through gestures, where a robot understands a pointing finger indicating an object or a wave. And interestingly, it can even involve nonverbal emotional expressions conveyed by the robot itself, perhaps through changing LED light colors on its body, synthesized sounds, or even subtle physical movements like a head tilt.
Robots showing emotion.
Or at least conveying state in an intuitive way. Social robots, like those designed as household companions or robotic pets, are specifically built to engage with people on a more personal, effective level. They often leverage cues like expressive eye-like cameras or friendly synthesized voices to seem more approachable and build rapport. A famous example is the humanoid robot Pepper, which was explicitly designed to converse and respond with simple emotional expressions, aiming to make it feel more like a companion than just a tool. The core idea is that robots need to be intuitive for humans to interact with, and achieving that involves as much psychology and thoughtful interaction design as it does complex engineering.
And what about working with robots?
Right. Another vital aspect of HRI, especially in industrial or service settings, is collaboration. Humans and robots actually working together on tasks side by side. In factories, modern cobots, or collaborative robots, are specifically designed to directly share a workspace with humans. They might assist workers in lifting heavy objects, holding parts steady, or performing precise assembly tasks without needing the traditional safety cages that kept old industrial robots completely separate.
How is that safe?
They're equipped with very sensitive sensors, force sensors, vision systems that allow them to detect human presence and stop immediately if a person gets too close or if an unexpected contact occurs, ensuring safety during collaboration. And this naturally leads us to an even broader, more philosophical yet deeply practical question within HRI. Beyond just functionality and safety, what about trust and robot ethics? How do we build systems that people trust to behave appropriately?
Trust seems huge, especially with autonomous systems.
It is. Robots must behave in ways that humans can inherently understand and trust. Think of a self-driving car, clearly communicating its intent to pedestrians through light signals before it proceeds through an intersection. Or an AI healthcare robot, meticulously preserving patient privacy and ensuring safety while assisting with sensitive tasks. The overarching goal of HRI is really about designing robots to seamlessly augment human capabilities and blend into the human world harmoniously and safely, building that essential bridge of trust and acceptance.
That's incredible to think about how complex even a simple interaction can be from the robot's perspective. Okay, we've talked a lot about what one robot can do, sensing, acting, learning, interacting. But what about the power of many robots working together? Can they coordinate as a team?
Absolutely. This is where we enter the really exciting frontier of multi-robot systems and swarm robotics. This whole area explores exactly that. How can multiple robots communicate, coordinate, and collaborate effectively as a team? The big question here is, how can a group of robots work together to achieve goals that are too complex, too large, or too dangerous for a single robot to handle alone?
So the power of teamwork, but for robots.
Precisely. When robots cooperate, they can accomplish tasks that a single robot alone simply couldn't manage efficiently, or perhaps couldn't manage at all. Imagine a team of drones autonomously mapping a vast, hazardous wildfire area simultaneously, covering ground far faster and providing a more complete picture than one drone ever could. Or picture a swarm of tiny, simple robots autonomously assembling themselves into a larger, more complex structure, maybe forming a temporary bridge or plugging a leak like self-building construction materials.
Wow, how do they coordinate? Do they talk to each other?
Yes, coordination is key. And the core ideas in this domain include robust inter-robot communication, where robots share information, sensor data, intentions, or signal each other wirelessly. And crucially, distributed coordination algorithms that dictate how they behave as a collective, ensuring they work together effectively without getting in each other's way or duplicating effort.
Can you give examples?
Sure. In a relatively simple case, two factory robots might need to coordinate their movements precisely down to the millisecond to lift a heavy, awkward object together, synchronizing their motions perfectly. In more complex swarms, say like 100 small, relatively cheap robots exploring a contaminated building after an earthquake, there might be no central leader, no single brain controlling them all. Instead, they follow decentralized rules, often bio-inspired by how ant colonies forage or flocks of birds fly in formation.
Like ants following pheromone trails.
Kind of like that, yes. For example, each individual robot might follow a simple rule, like maintain a certain distance from your nearest neighbors, avoid collisions, and move generally towards a potential victim's heat signature. And collectively, the group exhibits remarkably organized, seemingly intelligent search behavior without any single robot having the full picture or giving orders.
That's fascinating. Decentralized intelligence, what are the challenges?
Well, multi-robot systems have to deal with inherent challenges like communication reliability. What happens if a signal drops between two robots? How do they avoid radio interference if hundreds are operating nearby? And sometimes they need to form ad hoc communication networks on the fly as they move around, passing messages relay style. But the potential applications are huge. We mentioned search and rescue. Environmental monitoring is another big one. Imagine a swarm of underwater sensor bots spread across a coral reef, or tiny drones monitoring air quality across a city, gathering data much more comprehensively than a single platform could.
And what are the main benefits of using a swarm versus one big robot?
The big picture benefits are often scalability and redundancy, or fault tolerance. 50 small, inexpensive robots might perform a task faster and with significantly more robustness than one large, complex, expensive robot. Why? Because the swarm can tolerate individual failures. If one or two robots break down, the mission can likely still continue. If your one big robot fails, the mission is over. So algorithms for multi-robot path planning, planning paths for everyone simultaneously without collisions, task allocation, deciding efficiently which robot should do which subtask, and robust cooperation strategies are all incredibly active and important research areas. If we connect this to the bigger picture, the core idea is that in numbers, robots have strength. But coordinating those numbers effectively to work seamlessly and intelligently requires its own unique set of sophisticated techniques and profound systems thinking.
That's a mind-bending leap from a single intelligent robot to an intelligent collective swarm. But, wow, with all these incredibly complex, interconnected components, perception, planning, control, the physical hardware, learning algorithms, human interaction rules, swarm dynamics, how do you even begin to build a single working robot that does anything useful, let alone a whole fleet of them? It sounds like an extreme integration challenge, almost like trying to build a modern airplane from scratch, using parts designed by hundreds of different engineers who barely talk to each other.
That's a great analogy, and it highlights a core principle. Designing robot software architectures with proper abstractions and modularity is absolutely crucial for managing this incredible complexity. Without that, it quickly becomes unmanageable. Modern robots are often described using the term cyber-physical systems, which are essentially complex engineered systems where intricate layers of software interact seamlessly and in real time with physical hardware components. The digital brain is deeply intertwined with and directly controls the physical body and its interaction with the world.
So how do roboticists manage that complexity?
Well, to handle this inherent complexity, the field of robotics has smartly adopted and adapted many standard best practices from traditional software engineering. This includes things like modular design, really breaking down the robot software into distinct, well-defined, often interchangeable units. You might have a dedicated perception module, a planning module, a control module, a communication module, etc. It also involves the pervasive use of middleware for communication between these modules, acting like a standardized plumbing system for data, and adherence to standard frameworks that provide common tools and structures.
Middleware, like plumbing for data.
Exactly. A prime example, and one you'll hear about constantly if you delve into robotics research and development, is the Robot Operating System, or ROS.
ROS. Okay, I've heard that acronym.
It's a widely used open-source middleware, technically more of a meta-operating system or framework that provides a structured communication layer. It typically uses a publish-subscribe model where different parts of the robot software components, often referred to as nodes, can publish data streams, like sensor readings or computed paths, and subscribe to data streams they need, like motor commands or localization updates. This greatly simplifies the integration process. It allows different teams, or even different universities or companies, to develop components independently using standard message types, and then combine them relatively easily into a working robot system. ROS also comes with extensive libraries for common robotics functionalities, visualization tools, and drivers for a vast array of sensors and actuators.
So it standardizes how the pieces talk to each other.
Precisely. By using such frameworks and adhering to coding standards, developers can more easily share code, build on each other's work, reuse components, and ultimately accelerate progress in the field.
What about testing? You can't just build a complex robot and hope it works first time.
Absolutely not. Another critical aspect involves simulation and powerful development tools. Before you test anything on a real physical robot, which can be slow, expensive, and potentially even dangerous if things go wrong, researchers and engineers extensively use physics-based simulators. Tools like Gazebo, Weebots, or NVIDIA's Isaac Sim allow for prototyping robots and algorithms entirely in a virtual environment that mimics real-world physics. This enables rapid iteration, testing under varied and controlled conditions, things that might be hard or unsafe to replicate in reality, and even training AI models like those RL agents on massive amounts of simulated data before deploying them to the real world. Simulation is indispensable.
And you mentioned systems thinking.
Yes, part of a roboticist's mindset, or at least it should be, is a deep commitment to what we call systems thinking. This is the fundamental recognition that a robot's hardware design, its sensing capabilities, and its software algorithms are all deeply interdependent. You can't really design them in isolation. For instance, the exact placement of a camera sensor on a robot's head or the weight and inertia of a robotic limb can profoundly affect what algorithms are needed for perception or control and how well they perform. A heavier limb, for example, needs a stronger motor, consumes more power, and likely requires more sophisticated control algorithms to move precisely and stably compared to a lighter one.
So the hardware choices affect the software needed and vice versa.
Exactly. There's a tight feedback loop between mechanical design, sensor selection, and algorithm development. So, what does this all mean for building the robots of the future? Managing complexity is absolutely vital. Successful robotics projects rely heavily on well-architected software systems, robust development tools like simulators, and standardized frameworks like ROS that enable modularity and abstraction. As one robotics educator aptly put it,
Okay, so we've meticulously broken down that sense-think-act loop. We've explored all the big ideas that make robots tick, from their perception and spatial awareness, with things like SLAM, to their ability to plan paths, control their movements using kinematics and dynamics, manipulate objects, learn new skills from experience, interact safely and maybe even socially with us humans, and even collaborate in teams or swarms. We've also touched on the incredible engineering challenge of building their underlying software systems using tools like ROS. Now, let's zoom out. What does this all mean for us? What are the broader societal impacts and the thrilling, yet perhaps also challenging, future of this entire field?
well, as we've hinted throughout, robotics, particularly driven by advances in AI, is truly poised to transform industries and daily life on a scale we probably haven't seen since maybe the internet or the personal computer. And like all major technological shifts, this brings with it both immense opportunities and significant challenges that we as a society need to actively think about and address.
Let's start with the opportunities. What's the positive side?
On the positive side, increased automation and the proliferation of embodied AI could dramatically boost productivity across almost every economic sector. Think manufacturing, logistics, agriculture, healthcare, construction. The list goes on. This could potentially even reindustrialize economies that have seen manufacturing jobs move elsewhere over the past decades. Mark Andreessen, for instance, paints a vivid picture. He argues that we should envision hyper-automated alien dreadnought factories, almost entirely run by AI-driven machines, churning out goods with incredible efficiency. He sees this not just as an incremental improvement, but as a potential brand-new manufacturing revolution that could drive massive economic growth and perhaps alleviate some of the supply chain vulnerabilities we've seen recently.
Beyond factories, what about benefits for people more directly?
Well, robots can take over jobs that are incredibly dangerous, dirty, or just mind-numbingly tedious for humans. Think mining deep underground, cleaning up hazardous waste sites, performing repetitive quality inspections, or endlessly sorting packages. This can significantly improve human safety and overall working conditions. They can also perform tasks requiring superhuman precision or consistency, like microassembly of tiny electronic components or assisting surgeons in complex, minimally invasive procedures. And they enable potentially highly scalable services, such as the idea of 247 elder care robots that could assist our rapidly aging populations, providing companionship, monitoring health, and helping with daily tasks. This could extend human capabilities, allow people to live independently for longer, and even help address growing labor shortages in sectors like healthcare and logistics.
So augmenting human capabilities and tackling jobs humans can't or don't want to do.
Exactly. And indeed, some visionaries see robotics, particularly highly automated manufacturing, as a key way to bring high-tech production back to countries like the U.S., using robotic labor to compete where the advantage was once primarily cheap human labor abroad.
Okay, those are some significant upsides. But this is where we confront some critical questions, right? While the benefits sound immense, widespread robotic automation naturally raises serious concerns about job displacement for certain roles.
Absolutely. That's probably the most prominent concern you hear. Think of the potential impact on millions of truck drivers if autonomous trucking becomes widespread, or warehouse workers, whose tasks might be completely taken over by sophisticated warehouse robots and automated systems. It becomes absolutely crucial that we manage this transition thoughtfully, not by trying to resist the technology, because that rarely works in the long run, but through proactive measures. Things like robust worker upskilling programs, accessible continuous retraining initiatives, and actively supporting the creation of new roles that inevitably emerge alongside these technologies. We have to remember, past industrial revolutions followed a similar pattern.
Yeah, we saw similar shifts with the agricultural revolution moving people off farms, then the industrial revolution moving them into factories, and the information age creating whole new categories of jobs. Each time, old jobs disappeared, but new, often higher value jobs emerged. The transition can be painful, though.
It certainly can be if not managed well. Beyond jobs, there are also critical questions of safety and regulation. Robots operating autonomously in public spaces, self-driving cars, delivery drones, service robots in hospitals or airports must be held to incredibly high safety standards to prevent accidents and build public confidence. Regulators and engineers worldwide are actively grappling with how to develop comprehensive frameworks for certifying these systems, for rigorously testing them, and for verifying, for example, an autonomous car's decision-making process in all conceivable, often very rare edge case scenarios. How safe is safe enough? It's a tough question.
I mean, about privacy? Robots with cameras and microphones everywhere.
Another significant consideration, yes. Robots operating in our homes or public spaces may be equipped with powerful sensors, including cameras and microphones, raising valid privacy concerns about data collection, how that data is used, and the potential for surveillance. And of course, like any connected device, any networked robot could potentially be vulnerable to hacking if not properly secured. And a hacked robot, unlike a hacked computer, could have immediate and dangerous physical consequences in the real world. Security is paramount.
So jobs, safety, privacy, security. What else?
Societally, we also have to consider the human response and how we build public trust. We need to navigate between unrealistic hype about utopian robot helpers and equally unrealistic dystopian fears fueled by science fiction.
Right. The narrative often swings between Rosie the Robot from the Jetsons and the Terminator.
Exactly. And that's why there are concerted efforts within the robotics community focusing on robot ethics and human-centric design principles. The goal is to ensure robots behave transparently, predictably, explainably, and align with human values, fostering acceptance and ensuring they are integrated into society beneficially, not harmfully.
So looking ahead, what's the big picture vision? You mentioned Musk and Andreessen see this as huge.
Yes, many leading experts and tech visionaries predict that robotics will become truly pervasive in the coming decades, extending far, far beyond the structured environments of factories and warehouses. One particularly compelling vision gaining traction is the rise of general-purpose humanoid robots. Robots designed with a human-like form factor, 2 arms, 2 legs, hands that can potentially be trained for a wide array of tasks using the same learning techniques we discussed, effectively becoming a new type of universal worker that can operate in an environment designed for humans, use human tools, and move seamlessly between different jobs.
Like Elon Musk's Optimus, the Tesla bot.
That's a prime example of this ambition. Musk's stated vision for Optimus is a humanoid robot initially intended to handle dangerous, repetitive, or boring tasks, but with the grand long-term ambition of becoming a truly general-purpose, adaptable machine capable of doing almost anything a human can physically do. He's even suggested, quite provocatively, that Optimus could eventually be the biggest product ever in terms of economic value, potentially surpassing even Tesla's massive car business. And they're not alone. Companies like Sanctuary AI with their Phoenix robot, Figure AI, Apptronic, and others are also pursuing this ambitious goal of creating adaptable, general-purpose humanoid helpers.
A universal worker.
Exactly.
That's a profound concept.
It really is. And if robotics truly becomes the biggest industry in history, as someone like Andreessen suggests it might, we could witness a societal shift as profound as the computing revolution itself, or perhaps even more so. Think about that analogy again. We moved from a few incredibly large, expensive, specialized mainframe computers that only highly trained experts could operate, which are sort of like today's highly specialized industrial robots, to ubiquitous, relatively cheap, personal computing devices that are in every pocket, every home, every office, used by everyone. Tomorrow's personal robots, perhaps these universal workers or other forms, could potentially become just as common and indispensable, transforming almost every aspect of our lives, from home automation and personal assistance to logistics, elder care, manufacturing, exploration, and even creative endeavors. So understanding these core concepts we've discussed today, from perception and SLAM to planning and control to learning from data, human interaction, multi-robot systems, and the importance of robust software architecture, is absolutely vital. It empowers you, the listener, to not just witness this revolution passively, but to understand it, perhaps participate in it, and help shape its future direction, while remaining deeply mindful of the broader human context, the ethical considerations, and the societal impact in where all this technology will unfold. This isn't just about cool technology, it's genuinely about shaping our future society. Hashtag outro. This field is truly vast, isn't it? And incredibly exciting. It's such a deep well of innovation that pulls together so many different disciplines: computer science, AI, mechanical engineering, electrical engineering, material science, even psychology for HRI. But hopefully, understanding these big ideas we've unpacked, from how robots perceive the world and figure out where they're using SLAM, to how they plan their movements, control their physical bodies with kinematics and dynamics, learn new skills through RL or imitation, interact with us safely and intuitively, coordinate effectively in teams or swarms, and how their complex software is meticulously architected using tools like ROS, hopefully, that provides you with an incredibly strong foundation to grasp this unfolding revolution.
Yeah, it really drives home just how complex and interconnected it all is, and how progress is constantly being made in this absolutely thrilling interdisciplinary domain. We really hope this deep dive not only helps you appreciate the immense challenges and the incredible breakthroughs happening in robotics, but perhaps it even inspires you, to learn more, get involved, or maybe even contribute to the advancements that are bringing this embodied AI revolution to life. And maybe as you go about your day-to-day, consider this final thought. Imagine a future, maybe not too far off, where robots aren't just specialized tools locked away in factories, but active, adaptable participants woven into the fabric of our daily lives. From our homes to our workplaces, truly as common and maybe as flexible as a smartphone is today. What new societal norms will we need? What unexpected ethical dilemmas will emerge? And what incredible new opportunities will arise when physical AI is truly that pervasive, that capable, and that intelligent? Something to think about. Thank you so much for joining us on this deep dive into the world of robotics and embodied AI. Until next time, keep exploring, keep learning, and definitely keep being curious.